Okay, hi everyone. Okay, today we from group 9 will explain about IIR filter design. Okay, this is the digital filter design. What is filtering? Filtering is process of changing signal spectral content, or we can say attenuate a range of frequency, or in a simple word, to remove unwanted frequency component from signal. Okay, we got two filter, which is one is IIR filter, then we have another one is FIR filter. So for Z transform, IIR filter, it convert from analog filter to digital filter, and also we can obtain different equation from IIR filter. For FIR filter, the Z transform with different equation can be obtained from time domain convolution. But for DTFT, both can analyze spectral response. This one also can analyze spectral response.
Okay, so now we'll talk about ideal filter. So there are four types of ideal filter, which is the low pass filter, high pass filter, band pass filter, and the band stop filter. For low pass filter, the graph is so this is the amplitude, this is the frequency, so this is cut-off frequency, and this is pi. So as you can see, low pass filter, it allows frequency that is lower than the cut-off frequency to pass through, and more than that it will be filtered out. So the equation is so as you can see from here, it is 1 when the frequency is less than or equal to the cutoff frequency, that means this region. And it is 0 when it is between the cutoff frequency and pi, which is this region. Second, we talk about high pass filter, and the graph is okay. So what it means is that high pass filter is actually the opposite of low pass filter. It allows frequency higher than the cutoff frequency to pass through, which is this region, and lower than that it will be filtered out. So the equation is so as you can see, when the frequency is less than the cutoff frequency, it's actually 0, and when the frequency is between the cutoff frequency and pi, it becomes 1. Okay, and the equation you can also use 1 minus low pass filter, which means it is opposite of the low pass filter. Next, we'll talk about band pass, and the graph is so it's between cutoff frequency 1 and cutoff frequency 2. So what you can see from here is that it allows frequency from in between cutoff frequency 1 and cutoff frequency 2 to pass through. Other than that, it will be filtered out. So the equation is so what you can see from here is that the amplitude becomes 0 when the frequency is less than the cutoff frequency 1, which is here, and the amplitude is 1 when the frequency is between cutoff frequency 1 and cutoff frequency 2, and it becomes 0 again when it is between cutoff frequency 2 and pi. And the equation is, or you can also use this equation. The low pass of cutoff frequency 2 minus the low pass filter of cutoff frequency 1. Next, we'll talk about band stop filter. So the graph is cutoff frequency 1, cutoff frequency 2. Oh my god. So what you can see from here is that it allows frequency less than the cutoff frequency 1 to pass through, and more than the cutoff frequency 2 to pass through. Between that area, it is 0. That means it is filtered out. So you can see the equation is as you can see from here, amplitude is 1 when the frequency is less than the cutoff frequency 1, and the amplitude becomes 0 when the frequency is between cutoff frequency 1 and cutoff frequency 2, and the amplitude becomes 1 again when the frequency is between cutoff frequency 2 and pi. And you can use this equation as well. Pass of cutoff frequency 2 plus low pass of cutoff frequency 1. Thank you.
Hi, good evening. I'm Mantu. So now I will explain about what is a non-ideal filter. So as you can see, I have drawn two graphs here. So one is about the non-ideal and one is about the ideal. So I want you to observe is about the two main difference between the non-ideal and ideal filter here. So the first one will be the slope here. Okay, slope. So as you can see, this is we call the transition band. So as you can see in the ideal, the transition band is a straight line which is equal to infinity. Transition band infinity. For this one, you see it has a value. It is not infinity. It is because in practical we are impossible to achieve to infinity transition band. So in order to monitor the slope of the transition band here, so you can always use about the higher order of filter. So when we use higher order of filter, the slope tends to be greater and more closer to the ideal. This is what we can achieve in practical instead of the straight line in ideal. So the second main point is about the ripple. As you can see in the ideal filter here, it don't have the ripple. So the ripple is basically caused by the noise, which in practical there is many noise around, especially when we build up the second order or higher the filter, it will always cause ripple inside the filter. So as we can see, we cannot obtain a straight clear signal like ideal in the non-ideal filter. Okay, so let's come to about some summarization of our video today. So basically, the IIR filter design divided into impulse variance and bilinear transformation, the two common techniques. Yeah, so for bilinear transformation, we will be explaining the chapter further later. So I just want to say about one similarity between the two techniques, which is from the S plane to the Z domain. So all the S poles are mapped onto the poles on S domain are mapped onto the Z pole. The poles on Z seg domain, yeah, seg host. So so this is HS is a continuous time filter, continuous, and seg domain is a discrete time. Alright, that's all for our video today, and I do hope you can really have a better understanding on the filter after this video. Thank you very much.